Okay, 4.2 is more on the polynomial functions that we talked about in 4.1. It's continued, basically. And it's continuing trying to further understand their graph. So in the last one, we looked at even and odd symmetry and extrema, max, mins, local, and absolute. And so now we're going to look at it's going to be kind of a global and localized thing too. We're going to look at the end behavior, what's happening at the tails of my graph, and then kind of what happens in the middle of my graph, all right, the turning points, the max and mins. All right, so we're going to, and the leading term of the polynomial is going to be the guy that's going to tell me what's happening. All right, so remember what a polynomial is. A polynomial is a function of degree n, where I've got some number times x values, where my exponents have to be non-negative, so positive integer values, a whole number, positive values. And that's going to be the important guy, the leading coefficient, the highest degree, which would be the degree of my function. Right, polynomials, remember, are both smooth and continuous. There's no whole gaps and asymptotes, no sharp corners. It's nice and smooth. No abrupt changes. Right, so then you can graph it without lifting your pencil. And again, that's important about quadratics. All right, so understanding their behavior, that's what we're looking for in this section. And so I graphed a couple of functions. So the first one I've got graphed here, which might be actually in the opposite order what's on yours. So I graphed a typical cubic where my leading term is a positive value, right? That A is my leading term. A is my leading term. And so it's a positive leading term. And so here's the graphs that I actually plugged in. So this would be the degree. So it's a cubic because my degree is 3. And so there's the most basic one. And then I manipulated a little bit, and those are the different colors that are showing up. And so the first graph is sort of a localized graph. All right, what's happening locally? Well, I can look locally and see where a few of my graphs have localized minimums and maximums. Maybe the blue one and the black one don't. They might not have max and mins, but the red, green, and light green color looks like they have extrema. But then when I zoom out, all right, so this is zoomed in near the origin, so the details of the graph happen near the origin. And then I zoom away from the origin. So if you'll see, my window's much bigger here. I went out to 1,000 in both the y directions and 20 in the x directions. And if you look at this, the graphs look like they're right on top of each other, right? They have the exact same shape towards their tails, right? So again, they're looking like they're behaving the exact same way when I zoom out. Locally, they're not. They're a bit different when I look in here locally. Some of them have extrema, some of them don't. The extrema is located at different places. But the tails of my graph are the same. Both functions kind of look this way, even when I look at the local and the absolute, or the global one, is it has my function shooting off to positive infinity on one side, negative infinity, and all 5 of my graphs do this. And so that's what we're going to get into. Kind of what's happening locally and what's happening globally. All right, so this is the graph of a typical quadratic. So a typical 4th degree polynomial. Quartatic, not quadratic. Again, my leading term is positive, so I picked the positive version. My leading term is positive. So again, if you look here, these are 4th degree polynomials where I've manipulated them a little bit, but they're all 4th degree polynomials. This is when I look close to the origin, so this is the zoomed in look. And again, close to the origin, they're very different. Extremely different, but they're a little different, right? My blue ones and my red and my green one looks like they might have minimums, but the black one doesn't. All right, the black one, or if it does, it looks like it's in a completely different spot. And so, looking here, they're separate and varied. But when I zoom out, right, this is my zoom out, you can barely distinguish the difference between them, right? They're behaving the same way. Both tails are shooting off to infinity in these cases. And so the tails of the graph are behaving the same way. In the middle, they're not. So here, towards the origin, they're different. But as I'm shooting off to the infinities, the shape's the same. And that's kind of what we're going to get to here in this section. And so what this is, again, trying to illustrate is that if you look at these, I started off with a basic function and then I added parts to it. All right, same thing on this one. I started off with a basic function and then I added more complex parts to it. What they all have in common is the same leading term. Right? They all have the same leading term in common. Right? They all have the same x to the fourth or x cubed. And so that's what this first rule is. If I've got a polynomial, so there's my original polynomial, and I put really big values of x either in the, so I'm shooting off to the positive infinity or the negative infinity, right? Put really big values of x in either the positive or the negative side. What happens is the graph of the function behaves like the leading coefficient. So what happens is this guy is growing so much bigger so fast, it overwhelms all of these guys and they don't matter. Right? So even though it's got more complex than that, the shape of the end behavior of my graph is the same as the end behavior of if I just looked at the leading term. And so that helps me out. That means all I have to do is know what the leading term is doing, and that'll tell me what my end behavior is doing. So if I plug in really big positive numbers, do they stay really big positive numbers? If I plug in big negative numbers, do they stay big negative numbers? And so the graph of the polynomial, the leading term, tells you the end behavior of the polynomial. Means when I plug really big values in for x, as x shoots off to infinity or x shoots off to negative infinity, all I have to know is what happens to the leading term, and I'll know what the function's doing. So when I plug in really big numbers, positive, do they stay positive or do they go negative? If I plug in really big negative numbers, do they go positive or do they go negative? Right, and all I have to do is look at my leading term to figure that out. And so that's what we're going to get into, all right, the end behavior and the turn. So end behavior is again, the tails of the graph. What's happening when I zoom out. The other thing we're going to look at is the turning points, and that's what's happening close to the origin. What's my maximum and minimums, and so that's what we're going to turn. So the turning points of a function is when the graph changes direction, all right, when you're switching from increase. So again, if I have a graph like this, I've got 3 turning points, right? Because I'm switching directions. It's turning. It's going from moving up to moving down or vice versa. And so those would be where I have my maxes and mins. And I can determine the maxes and mins, how many possible there are, based on my leading term. Right? And that has to do with the local part, what's happening locally, what's happening towards the origins. All right, so the turning parts is what's happening towards. So my maximum mins occur near the origin. My end behavior is what's happening outside the origin when I go zoom out and I look at the really big part, how that's in. But all of them can be at least guessed at or determined based on my leading coefficient. And that's what we're going to get into in this section. All right, so we're going to look at end behavior, turning points specifically meaning maxes and mins, and how we determine them based on that leading term and my degree of my function. All right, and that's what we're going to get into in this section.